Right, so this is the third part of the Paper 2 warm-up 2016 video. So far we've done electrolysis, we've done titrations, and we've done organic chemistry relating to polymers. So in this video I'm going to try and get through the question on aluminium extraction and on identification. So let's go for it. I'm going to have a quick swig of tea. Got a little bit of a sore throat this morning, and let's crack on. Right, here we go. So here we've got a picture of the process used to extract aluminium from its ore, and hopefully you know the ore of aluminium is bauxite. And name the process used to extract aluminium. Well, that's a real giveaway question. I hope the process is electrolysis. And name the material used for the electrodes A and B. And the electrodes we would make out of graphite, because graphite is an excellent conductor of electricity. It also has a very, very high melting point, so we're using some very high temperatures in this electrolysis cell in order to keep the electrolyte here, the substance that is being electrolyzed, molten. So we need something that won't melt, and graphite is that kind of thing. Now, the next question asks us to identify the electrodes A and B. And initially, I always find a question like this confusing, but it helps me knowing if I identify the substance that's formed at the bottom as aluminium. Now, aluminium is a metal. Its ions that were floating around within the electrolyte are Al3+. So the Al3+ ions have made their way down to electrode B, which suggests that the charge on electrode B is opposite to whatever's on aluminium. So electrode B is negative, and that means electrode A must be positive. So the negative ions in our electrolyte are oxide. And notice the language I'm using here. I didn't say they were oxygen ions, I called them oxide, which is their name, and they'd be attracted to A. Now, what would happen to the aluminium when it gets to the negative electrode? Well, it would pick up electrons. It would collect 3 electrons, in fact, to form aluminium metal. And that's the kind of thing that you might be asked a question on. So Al3 plus 3E goes to Al. And what would happen to the oxide when it got to the positive electrode? Well, it would form oxygen. Now, oxygen has 2 oxygen atoms in it, so it'd be O2. Writing is even worse than normal today. Now, as we need 2 oxygen atoms to do that, we need 2 oxides. And now the charge on the left-hand side of this equation, because we've got 2 of them, is 4-. So I would put 4- charges on the right-hand side. Sorry. So we've got 4 electrons there, and notice that very small negative charge. So those are the 2 half equations for the process. The aluminium is being reduced because it's gaining electrons, and the oxide ions are being oxidized because they are losing electrons, they're kicking electrons out. So, name the 2 compounds present in liquid C. So, in the electrolyte, we have a substance called cryolite. Okay, and we also have aluminium oxide. Those are the 2 compounds we have present. Now you might be thinking, well, why bother having any cryolite in there? Well, aluminium oxide, well, for a start, the electrolyte needs to be liquid, because otherwise it won't conduct electricity. The ions within it cannot move if they're held together in a lattice. So one option would be to melt the aluminium oxide. But aluminium oxide has a very, very, very high melting point. It's also, so you might then say, as a solution, oh, okay, well, what about dissolving it in water? You can't do that with aluminium oxide. It doesn't dissolve in water. But it does dissolve in this substance called cryolite. So if we melt the cryolite normally is a solid, but if we melt it and then we put aluminium oxide in, it dissolves. And so we can have an electrolyte with mobile aluminium ions and mobile oxide ions in. And it's the aluminium ions we're really interested in being mobile. And therefore it is a bit cheaper than if we were doing it with pure molten aluminium oxide, because we're using lower temperatures than we would have to use there. They're still pretty high temperatures in fairness, but they're lower than if it was pure aluminium oxide. Now the next question is state one major cost. Now please don't put more than one down, it's only asking for one. So a major cost, okay, is the large amounts of electricity. So you often find aluminium extraction plants built near power stations. Another major cost is actually the high temperatures. Okay, whereas actually, it's probably not the temperature itself, it's the fuel needed to keep high temperatures to ensure the cryolite is molten. If a question asks you why cryolite is needed, please don't say it lowers the melting point of aluminium oxide. It doesn't. It is a solvent, effectively. The melting point of aluminium is still incredibly high. It doesn't lower the melting point, it just provides a solvent for the aluminium oxide to dissolve in. Now I'm hoping this works, because I've gone back to this slide. So at compound A, at electrode A, it says we have a compound formed and we have an element formed. Well, we have an element formed, we've already talked about that, oxygen. And this process is going on at very, very high temperatures. So the oxygen that is bubbling off around these electrodes reacts with the electrodes themselves. And the electrodes are made of graphite, which is carbon. So we also get carbon dioxide being formed. And that's a bit of a pain for the people doing this process, because it starts to wear away at the electrodes. The carbon which was there has been turned into carbon dioxide and so disappeared, and so that erodes the electrodes. As the electrodes keep needing to be replaced over time. It's not a huge issue, because graphite, relatively speaking, in comparison to the amount of electricity being used and in comparison to the high temperatures being used, is relatively cheap. So let's have a look at putting that into the question. Now, at electrode A, we get an element and a compound being formed. And so identify the element is oxygen, identify the compound, and explanation, oxygen formed reacts with the graphite electrodes at the high temperatures in the cell. Good. I hope that's covered that. So onwards, and here is our identification question. So we've been given 5 possible compounds, and we have 4 solutions, which these obviously could be. So we've got to work out essentially which one is which. Now, solution A, you add sodium hydroxide to it and a pungent gas is given off. So pungent, very smelly, and the only pungent gas you've really come across is ammonia. And the presence of that ammonia gas suggests that in the original solution there were ammonium ions present, because the ammonium ions react with the hydroxide in the sodium hydroxide to produce ammonia and some water. So solution A is probably ammonium chloride. And that's confirmed to us because a white precipitate forms when dilute nitric acid and silver nitrate is added. So again, the question is asked quite cunningly: which ion must be present in A for the white precipitate to form? Now, if you say chlorine, you don't get the mark, because the ion there is chloride. And you might think, oh, I'll be cunning, I'll just write Cl. Well, that doesn't cut it either. If you write Cl, you have to put the charge on the ion, Cl minus. So we've identified A, and solution B has a blue colour, which probably will give you some quite clear clues about what it is, I hope. You add the solution to sodium hydroxide and you produce a beautiful blue precipitate. It doesn't mention that it's beautiful blue, but I'm hoping you remember doing this in the laboratory and you get that wonderful clear blue precipitate. What actually causes the blue precipitate to form? Well, it's copper ions, copper 2+ ions, and I think it's important to say the charge. And a question might ask for an ionic equation on this, and hopefully you can remember that you take the copper 2+ ions, which are aqueous, you combine those with hydroxide ions, which are also aqueous, and you form copper hydroxide, which is a solid. And obviously that isn't balanced, so you need a 2 on the hydroxides there. And the question then moves on to compound D. What ion must be present for the green precipitate to form? Well, green precipitate with sodium hydroxide, it's going to be a swampy, murky green. And the ion present for that to form is Fe2+. And again, the ionic equation, if they'd asked, is pretty much the same as this one, except we'd have Fe2+ instead of the Cu's there. Interestingly, if solution D, when it had been mixed with sodium hydroxide, had been left out for a little bit, the green precipitate would probably have started to turn brown, and that's because the Fe2+ ions within the precipitate are being oxidized to Fe3+ ions, and so the precipitate is no longer FeOH2 but is FeOH3, and that's a different colour. Anyway, I digress. Which compound in the list can be identified using barium chloride? Now, barium chloride is used in the test for sulfate ions, and here's the only one containing sulfate, so the answer is copper sulfate. State one compound in the list that can be identified using a flame test. Well, the most obvious one to me is the first one, which has got potassium. And when you put potassium in a flame test, you get a lovely lilac flame, or when I'm teaching this in lessons I call it I've misspelt it. Good grief. Let's see if I can rub this out. Oh, brilliant. A rare moment of efficiency, although it would have been more efficient if I hadn't made the mistake. I call it lilac. Okay, emphasising to the students that it's got a K at the end, so it's potassium.